Welcome back to our session. We're still looking into the experimental or the practical side of determining, internal resistance of a battery in the context of, an electric circuit. Now, what we've done in the previous segment, we've managed to look at a scenario where we use a rheostat to, vary the resistance, which, ultimately also affects the amount of current. So, in other words, changing the current that passes through the battery had no effect whatsoever on the magnitude of the internal resistance of the battery. So, we are saying that in many ways, the internal resistance of the battery remains constant. Now, we'll try and focus our attention on something that is different in terms of the approach of determining internal resistance of a battery. Okay, let's look at that. Right, so we still intend, or our objective is to determine the internal resistance of a battery by using a different approach altogether. Okay, now the question is, could you change the current passing through the battery? Okay, so we are changing current, okay, in the circuit by adding more identical resistors in parallel. Right, very, very important. If resistors are identical, we're saying that they carry the same, or they offer the same magnitude or size of resistance in the circuit. So if each one of them is 10 ohms, and then we've got multiple resistors that are identical, it means all of them are actually 10 ohm resistors, as an example, okay? So by adding more resistors in parallel to the circuit instead of using a rheostat. So we're substituting a rheostat by in other words, we're saying adding resistors in parallel has the same effect as that of a rheostat, adjusting the resistance value on a rheostat. So when we are determining the internal resistance of a battery, right? Okay, so we're going to add one 10 ohm resistor in parallel to them, and then take the voltmeter and ammeter reading. So we're still measuring current as well as V external. So this voltmeter reading is our V external in all the cases. We'll repeat the step 4 times. It means in each time we add a 10 ohm resistor in parallel. Okay, so that's the procedure. Right, so this is how the setup actually looks like. But as a starting point, we have got the switch that is open. When there is zero current in the circuit, okay, V external is equals to 6 volts, right? It's a given, okay? Now, if we continue, we add more and then we close the switch, okay? There is a current of 1 ampere that is passing through the battery, and that is split between the 2 resistors. Okay, take note, the 2 resistors are connected in parallel. Okay, but now our focus is just a different way, okay, of determining internal resistance. Think about that always, right? So this is the values that we obtained when the switch was open. So this was an open switch, okay? This was an open switch. There are a lot of implications in as far as the open switch. When there is zero current, the voltage across the battery was 6 volts. And then we kept on adding resistors. Okay, when there was 1 resistor, the reading on current was 0.55. Okay, the voltage value, V external, dropped to 5.45. And then you also need to pay attention. As we add more resistors in parallel, the amount of current increases, right? So if we are to look at the trend, okay, if adding resistors, adding identical, okay? So adding identical resistors in parallel, okay? Increases, current increases, okay? Current increases, that's an observation, while V external decreases, right? Okay, so this is the graph that we obtained, right? Still, it's a linear graph. Very important to note that this is a linear graph, because this has got other far-reaching implications in terms of interpretation. This is a linear graph. It means there is a constant gradient, right? There is a constant gradient. Right, and we know that the gradient of this graph actually represents the negative value of our internal resistance. Right, so this is the graph that was obtained, and then the question says, what effect does adding identical resistors have in parallel have on the current reading? Okay, now we know that current increased, okay? Current increases, all right? Because we are saying that adding more resistors in parallel, it actually decreases the effective resistance in the circuit. So when the effective resistance decreases, current is going to increase, right? But what happens to the voltage? V external decreases, right? Why did V external decrease? It's because there is lesser effective resistance in the external circuit, then there will be lesser voltage across it, okay? Right, so that's the trend. Now we want to use the graph to determine the internal resistance. Now we're going to identify 2 points in the graph that we can use to determine the gradient, okay? We'll use that point, and I always prefer the intercept because it makes life much easier, right? So the 2 coordinates that we have, the first one, it's 0, 6. So when there is no current, the voltage across the battery was 6 volt. And then we'll also want to use the other value, which is 1 and 5, okay? Right, so the gradient in this case is equals to change in y, which is 6 minus 1, okay? Over it's actually 6 minus 1 minus 5. Okay, let's correct that because it's changing y, okay? Right. So interpretation is very, very important. So it's 6 minus 5, okay? And then 0 minus 1, okay? So this gives us minus 1. And we know that this gradient of minus 1 actually represents the internal resistance. So the negative gradient represents the magnitude of internal resistance, which is 1 ohm, okay? Which is the very same value that we obtained, okay? So we've managed to do that using the graph. So this is a calculation problem. So what are we saying? We're saying that the alternative method of changing the current passing through the battery by adding more identical resistors in parallel, okay, to the circuit instead of using the rheostat actually produced similar results. In the first case, we got internal resistance of 1 ohm, okay, while we were changing the resistance on the rheostat, and while we add identical resistors in parallel, we also achieve the same effect of decreasing the effective resistance. So what does this say to us? It says, indeed, this method does confirm that internal resistance of a battery is ohmic. Right, let's put that into context, okay? We are saying that no matter how much we vary or we change the current that passes through the battery, that has no bearing on the magnitude of the internal resistance of the battery, right? But more important is that, the resistor inside the battery or the internal resistance of a battery is actually an ohmic type of a resistor. What does it mean? It means that it obeys the Ohm's law, which is why we actually managed to get that linear graph, okay? So the linear relationship that exists there suggests that, yes, indeed, the internal resistor inside the battery is actually an ohmic type of a resistor, right? So that's very, very important. So internal resistance is treated like an ohmic resistor, right? We are happy with that. We've also managed to say that, yes, indeed, the intercept, when there is 0 current, actually represents the internal resistance. And we've managed to use the gradient to calculate the magnitude of the internal resistance of the battery. So these are some of the questions that you need to ask yourself in a way to try to understand the concept of internal resistance. With that said, that's the time we had for today. See you next time.